So thank you again. So in the first one, we took very conventional accelerometer where the straight beam was changed to curve beam. Now we will go into the different types. The question is, let us say if you want to achieve how to increase the, let us say, signal to noise ratio. Either you increase the displacement or you increase the change in the capacitance by increasing the number of combs, right? Then only things will improve. But for conventional, to do that, you have to keep on increasing the mass, proof mass, and the number of holes and all. So alternate is, can we use amplifier which is mechanical based amplifier, not electrical based? So this particular work is based on that. So I'll talk about what is compliant displacement amplifier, which uses compliant mechanism, and then so different uh, uh, types of compliant mechanism. Then we have also optimized that amplifier using genetic algorithm based algorithm. And then we have performed sensitivity and bandwidth analysis. And after that, we have also introduced closed loop analysis in this particular. So first of all, what is mechanical amplifier? So here, if you see, basically, now, so this is fixed here. If let us say I apply an input this side, and if I measure it again at the same position, you will see that you get more or less the same change as an output. But if I use the output somewhere away from here, so you will see that a small deflection here may give you large deflection. So there is an amplification happening due to the lever mechanism. Okay, so this is the concept, and this is your conventional type. So now let us try to see what are the different amplification. One is called lever based that I just explained. Another one is called compound lever based, where you can use your multiple levers to attain that. Then there is a bridge type, and then you have a lever bridge type, combinations you can have. So we have designed almost all 4 or 5 kind of design, but this particular work where you will see that. So before going into this amplifier, so such kind of accelerometer contains 2 components. One is called the proof mass one. So this is your proof mass conventional portion. Then you will put here the amplifier after you design it, and this amplifier will give more displacement to this sensing proof mass. Okay. So this is drive proof mass and this is sensing proof mass. So here what really happens, if delta is the input to the amplifier, you will get some 10 times delta or 100 times delta based on what kind of amplifier you're using. It means the deflection over here is more than what you would have achieved in the conventional one. Now you will see if you put the footprint area same, so you can use in that footprint conventional. Alternate is the this kind of accelerometer. So you will see that such kind of accelerometer works out quite well. And again, those things I'll talk about later, but let me first explain. So this is one type of accelerometer amplifier. So very simple amplifier. If you want to use, you can have all these member as a straight member. Okay, this, and this. So if you apply input here, what you are getting at this particular end is the output. Okay, so we have done 3 major changes. One, all these members we have replaced with the curve. And second, here there used to be the rigid one where we have put here one folded kind of arrow-shaped beams. So what will happen? So if it goes like this will get deflected, and when this get deflected, uh, so this eventually will go up, and then the beam, the sensing part is connected to this particular limit. So ultimately you will get a deflection at this particular end, more amplified one. So related dimensions are mentioned over here. Now this is what we tried to optimize Now, for if you want to find out the K effective, M effective, then damping and capacitance for the whole structure, these are the formulas that, and these are the lumped model that one can make. So this N is to 1 ratio basically tells you how much is the N times kind of deflection, sorry, amplification you will be getting using this compliant mechanism. Will not go more detail into it, but this is what the optimization we used for optimizing the parameters related with our amplifiers, and these are the two limits that we kept. So between that, the optimized version, we did the error analysis. We can see that the variation is quite low, and then there's also delta C change that we got. So here, a natural frequency variation 1% and capacitance change 4% we found. So based on that, we optimized the amplifier and all. And we took that particular design to MEMS Plus, and this is how we made it over there. So last design you saw is simply this bottom one. Now you have this amplifier which is sitting, and this will deflect this. And there are a lot of combs here. Earlier the number of combs were less. So all combs can be used for the sensing kind of application. And this is how you can see. Basically, the small deflection over here, you can see how flexible it is, and it will give you a large push at the end, and a lot of deflection can be chased. So over minus 30 to 30. So earlier one you can saw the range was limited, minus 10 to 30. Here we can go for a little higher range, minus 30 to 30. Where the displacement of the proof. This is your proof mass. This is your sense mass. Can be seen over here. Of course, the sense mass deflection is increased, and this is the corresponding change. So one is C1. C1, as I said, uh, this combination of fixed and moving combs. One comb will come closer to one of the finger, and another one will come go away from. So you see this C1 and C2 going opposite, but the delta C that you get is what. So it will be around 500 femtofarad level that you achieve over this range of minus 30 to 30. And then again, tolerances that we did from minus 1 to 1. So what will be the frequency change? What will be the deflection change that you will be getting? Then base capacitance may also vary. So we found that with these, and this is your quality factor changes. After that, we followed this process of SOI and again made this model. So first we made open loop analysis where the conversion to voltage was done. And then this is the circuit basically in the open loop. And so this is what it does. Just nullify the offset, then it do the low pass filter here, high pass filter here, and ultimately you get the V out. So here you can see this is the transient, and this is for the step input, which is your acceleration of 1G, which is being given, and this is your output, which you can see. And there is improvement in the bandwidth, not too much, but a little bit with the help of DACM. Then there's a closed loop analysis where the controllers are controlling force is being given to the proof mass. Okay, here controlling force will be given to the lower proof mass to control the sensing thing. And this is the results that you can see. So input signal sinusoidal is being given, and this is output. So MEMS plus and analytical model both are being used. Lump based model is analytical model. MEMS plus is the numerical. And you can see that there is a difference here, obviously, because the design is a little complicated. So then we compared this particular linearity, the variation of this V out between open loop and closed loop. And you can see that with the closed loop, one can maintain linearity over a large range, and that's how it becomes quite useful. With this would like to thank you.